Good morning, good afternoon, good evening, whatever the case may be. We are back in better than ever, and today we are finishing up our study of sequences and series with geometric series. So let's get to it, shall we? All right. So, as with arithmetic series, a geometric series is a sum of the terms of a geometric sequence, right? So if we have a geometric sequence that is finite, that is, that it ends, we can certainly add up the terms and we get the geometric series. Okay, so all of these cowboys where the common ratio is 2, I can add up and I get the geometric series. Okay, so the sum of a finite geometric series is given by either of these two formulas. They're the same. It's just a matter of whether you want to take the common ratio to n and subtract 1, or take 1 minus the common ratio to the nth power to help me, to find the sum of the terms of the sequence to get the series. Okay, and there is a nice little proof here. If you'd like to read through it, we can talk about it in class as well. But I want to get right to it here. Find the sum of blah, 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 that geometric sequence to 12 terms. Okay, so that's finite because they're saying find the sum of the first 12 terms. So, of course, we could list the first 12 terms, but what a pain that would be. Not much of a pain, but if we have a nice formula, we can use it. So here we are, the sum of n terms of a finite geometric sequence. So we know that S sub n is equal to u sub 1 multiplied by r to the n minus 1 all over r minus 1. Okay, so the common ratio is the ratio between any two consecutive terms. So I'll go with 18 compared to its previous term 6, and that is equal to 3. So we have the first term 2 times the common ratio 3 to the 12th minus 1, since we're doing 12 terms. I guess I should have put S sub 12 here, the sum of the first 12 terms, all over r minus 1. And you would crank that on a calculator and you would see that that is equal to 531,440. Easy peasy. Okay. What about this one? Find a formula for S sub n for the sum of the first n terms of the series 9 minus 3 plus 1 minus 1/3, on and on and on. So this would allow us to find the sum of however many terms we wanted in the geometric sequence, and if we named a number of terms, it would of course be finite. Okay, so we know that, I'll go ahead and use the second one this time. So we have S sub n, this is the formula we're going to use, equals u sub 1 times 1 minus r to the n power all over 1 minus r. Okay, so all we need is u sub 1, which is equal to 9, and the common ratio, which would be the ratio of a term compared to its previous term. So r is negative 3 over 9, which is negative 1/3. So this is very, very simple. So this would be equal to 9 times 1 minus a negative 1/3 to the n power all over 1 minus, common ratio is negative 4/3. No, it's not. It's negative 1/3. I was getting ahead of myself. So this would equal 9 times 1 minus negative 1/3 to the n. Don't you dare say, oh, this should be positive, because our order of operation dictates that we would have to take care of the exponent first, which we don't know. So this becomes 1 plus 1/3, which is 4/3, and 9 divided by 4/3 is equal to 27 over 4. And then I can write it like this if I'd like. 1 minus a negative 1/3 to the n power. Okay, so there you have it. You could use this formula to find the sum of any number of terms of this particular geometric series. Okay, all right, so what about an infinite geometric series? So it's not n terms, it's a whole bunch of terms. Okay, so if we have a term, if we have a sequence where the terms are continually increasing, well, that's just going to keep going and going and going, and it's going to get infinitely large. So we cannot find the sum of a geometric series, an infinite geometric series, where the terms are continuously increasing. Okay, so that occurs when the common ratio is greater than 1. With the absolute value here, what they're saying is r would be greater than 1, or r could be less than -1, because the absolute value would take care of that. So if our common ratio is greater than 1 or less than -1, we can't find the sum. Okay. However, if the absolute value of r is less than 1, which means -1 is less than r is less than 1, then we can find the sum. For example, if r is 1/2, we get 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, and we keep going and going and going and going. And if we go to infinity, if we can think of it going to infinity, this sum is getting closer and closer and closer to 2, where it does indeed equal 2. Okay, so if we have this case where r is a fraction where the numerator is less than the denominator, so that would be between -1 and 1, it will converge to this sum. We say it converges. It gets closer and closer and closer. And we can use this formula to find it. I'm going to do an example, then I'm going to try and show you that on a spreadsheet. Write 0.7 repeat as a rational number. Well, we know that 0.7 repeat is equal to 0.777777 forever and ever and ever. Well, that's also equal to 7/10 for this first term right here, or this first decimal place, plus 7/100 for this one, plus 7/1000, plus boom, 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 forever, and we could just go on forever and ever and ever. Well, boys and girls, that's actually an infinite geometric series, okay, where u sub 1, our first term, would be equal to 7/10, and our common ratio would be, just take any term, 7/100 compare it to the previous term, 7/10, and that is equal to 1/10. Okay, so the sum to infinity is equal to u sub 1 over 1 minus r. This is where it will converge. Okay, and since r is between -1 and 1, then I can find the sum. So this would be equal to my first term, 7/10, over 1 minus 1/10, which is equal to 7/10 over 9/10, which is equal to 7/9. Okay. All right. So now I said it's kind of a weird concept. Okay, but I'm going to go back here to this little geometric series where the common ratio is 1/2. And I want to show you on a spreadsheet how that will get closer and closer and closer. We say that it converges to 2. So let's have a look. Okay, so I'm going to get those terms first. So I'm going to make this 1. Okay, then I'm just going to throw in a formula here where I can get a bunch of terms. Okay, so that's 0.5. And I know I have a lot of decimal places, but you'll see why in a second. Okay, oops. pull this formula down, and I'll just do the first term. So this is 1, 1/2, 1/4, 1/8, and 1/16 is decimals. And I'm going to get the sum of that for you. And I'm just using a spreadsheet formula. And that's equal to 1.9375. Then I'll go to 10 terms. Okay, so it's just multiplying the previous one by 1/2. And now I'm going to get the sum of those 10. Okay, and let's see what happens. Oh, it gets really darn close, right? 1.998. And now I'm just going to take this down for as much, maybe the first 32 terms there. Okay, and I'm going to get the sum for us equals sum of all of those, and let's see what we got. And it gets, eventually it gets to 2. It just gets closer and closer. Let me do this. Maybe we can get something in between. This is probably going to be 1.9999999. We'll see. Yep, you see 1.999999809. And eventually it gets closer and closer and closer to 2 until we say it eventually equals 2 if we take an infinite number of sums. And again, that's why we can use this formula to find the sum of an infinite geometric series as long as the common ratio is between -1 and 1. All right, that's all I got. I hope you enjoyed it. Let's get some tunes to take us out. And with that, I am out.